The controller they're having problems with around here.
This controller looks a little different than the controllers I've worked on before.
Now, probably this one's a little bit newer than most of the ones I have around here. Now, since the system's on manual, this controller doesn't affect the process, so I can vary the input and see how it responds. That's the one we're having trouble with, all right. See, I can change the input, and the output remains the same. It seems to be plugged up. I'll have to take it back to the shop and check it out. Now, because this controller is new to you, I want you to look over the manufacturer's data before you start trying to fix it.
Okay. This is the part that needs to be replaced.
Okay, look up the part number, then go get it from the stockroom.
Right.
Now, this apprentice has been working on pneumatic instrumentation for some time now, so he pretty much knows what we've got in our plant. But manufacturers do come up with something new from time to time. A little improvement here and change there. Now, if he knows his basics, he should be able to look through the manufacturer's technical material and repair an instrument that he's never seen before. He can do this because most pneumatic instruments have in common basic components and structures. And even though they may look different, their operation is often quite similar. And what we're going to do in this program is give you the basics of pneumatic instrumentation. But first, let's look at some of the different categories or types of pneumatic instruments you may work with. This large block stands for any process variable, such as temperature, pressure, level, or flow. Now, we're going to add a number of figures that represent the different categories of pneumatic instruments, which are typically found in pneumatic instrument control system. For example, this first figure represents pneumatic instruments that have a transmitting function. They produce and transmit a pneumatic signal that represents the value of a process variable. Two types of transmitters are a blind transmitter, which produces and transmits a signal that is proportional to the value of the process variable, and an indicating transmitter, which not only produces and transmits a signal, but also indicates the value of the process variable. Transmitters are able to determine the value of the process variable by input they get from devices or primary elements that perform a detection function. That is, primary elements detect or sense specific types of changes in the process. Sometimes these elements are part of the transmitter. For example, a bourdon tube is often part of a transmitter. The bourdon tube in this transmitter senses changes directly from the process. However, primary elements can be separate from the transmitter. For example, a temperature bulb inside this pipe detects a temperature change and converts it to a change in pressure, which in turn is detected by another sensing element inside the transmitter. In this example, the primary element is a displacer inside this pipe. It's used to convert level changes into a mechanical motion that can be measured by this transmitter. Another primary element is an orifice plate inside this pipe, which converts flow into differential pressure that can then be measured by a transmitter. So, primary elements detect changes in process variables. Transmitters measure the value of the changes and transmit pneumatic signals that represent those changes. The pneumatic signal that the transmitter produces is actually air pressure that has a force that can range from 3 to 15 psi 3 to 27 psi, or any of several standard signal pressures. It's important to remember, though, that the signal represents the actual value of the process. And of course, the transmitter transmits its signal to other types of pneumatic instruments that perform other functions. Now, let's see what some of these other functions are. Some instruments perform an indication function. Indicating instruments use air pressure signals to operate a mechanical device that produces a visual indication. For example, this is a common gauge. It has a graduated scale that indicates the value of a measured variable in units of psi, or pounds per square inch. Other gauges may indicate in units of feet, degrees of temperature, gallons per hour, or some other unit of measurement. These are draft gauges. They're often used by system operators to monitor various process pressures throughout the plant. While a transmitter can send a signal to indicating instruments, it may also transmit its signal to pneumatic instruments that perform a recording function. The recording instruments not only visually indicate the present condition of a process variable, but they also maintain a record of the value of the variable over a period of time. For example, this is a single-point recorder. It's a single-point recorder because it's recording the value of only one variable. This is a multi-point recorder. It's a multi-point recorder because it's recording the value of more than one variable. In addition to sending a signal to indicating and recording instruments, a transmitter may send a signal to associated instruments that perform a protection function, such as alarms that warn when a process variable has changed beyond desired limits, or pressure switches that bring in a backup safety system when a process variable reaches a critical point. So a transmitter may send its signal to indication, recording, and protection instruments. In a process control system, it also transmits a signal representing the condition of a process variable to an instrument that performs a controlling function. Controlling instruments measure the signal, compare it to set point, compute the difference, and produce a correcting signal. For example, this is a controller. It can be used to regulate process variables such as temperature, level, pressure, or flow. The output signal of controllers can be adjusted to provide a variety of control actions, including proportional, reset, rate, or a combination of these control actions. The signal from the controller is frequently sent to another type of instrument called a control station. A control station allows an operator to control a plant condition manually if necessary. For example, this operator has switched a control station to manual so he can manually control a specific process variable. However, under normal operating conditions, the controller's signal merely passes through the control station on its way to a final control element. Final control elements are instruments that perform a manipulating function. They manipulate a process variable in some way so that the controlled variable is maintained within a desired range. For example, this is a diaphragm actuator and positioner. Together, these instruments use the signal from a controller to position a valve, adjusting the flow of liquid through this system. Here, a piston actuator and positioner located inside this housing are used to position louvers in an air duct, adjusting the flow of air. What we've seen then is that pneumatic instruments perform a variety of functions. They can be used to detect, transmit, indicate, and record the value of process variables, as well as controlling and manipulating the same variables. As we'll see, these instruments have self-balancing mechanisms that help them to work automatically. We'll look at what is meant by the term self-balancing when we continue with the next part of this program. But for now, read the material in your text. So how's it going?
Not as hard as I thought it'd be. Really, this controller isn't much different. it still has the same basic mechanisms. They're just built a little differently.
Now you're catching on. Now this apprentice brought up an important point. Pneumatic instruments like controllers, transmitters, and positioners have common mechanisms, and it's the arrangement of these mechanisms that make these instruments self-balancing. But what is meant by self-balancing? Well, I can show you basically what it means using this weight scale. Now here we have two trays suspended from a beam. Now, the beam is pivoted in the middle so that when an unknown weight is placed in this tray, known weights can be placed in this tray to bring the system into balance. A pointer indicator has been added to the weight scale so we can tell when the two weights are balanced. Now let me demonstrate how this instrument works. Let's say I've got a piece of metal and I want to find out how much it weighs. So I place it in this tray. Now, in essence, I've applied an unknown input to our instrument. So let's identify this tray as our input mechanism. As you can see, the scale's obviously out of balance. Well, now I'm going to add these known weights to this tray to try to bring the mechanism back into balance. I'll call this tray the output or balancing mechanism. To determine if the scale is exactly balanced, we look at the pointer. As you can see, it is off. In other words, the system's not in balance. It's in error. Now, I'll identify the pointer and scale as an error detector. So now I'll add another weight to try and bring the scale into balance. There. Now all I have to do now is add the known weights. 20 plus 20 plus 10 or 50 grams. So the unknown piece of metal weighed 50 grams. Well, now how does this relate to pneumatic instruments? Well, pneumatic instruments work on the same balancing principle. Now, this scale was pretty useful in describing the balancing concept, but you're not going to see anything like this inside an instrument case. For one thing, the scale works with weights, but pneumatic instruments typically work with pressures. So let's look at a similar example that more closely resembles a pneumatic instrument. In this illustration, the trays of the scale have been replaced by two bellows. We also have a balance beam, a pivot that's centered between the two bellows, and an error detector. Now, when an unknown pressure is applied to the input bellows, it expands, creating an imbalance that is indicated by the error detector. So how is this error corrected? Well, with the scale, we added weights to the output tray until balance was restored. Now, in the pneumatic instrument example, we apply pressure to the output or balancing bellows until balance is also restored. Now here we've added an air supply and a manual control valve. If we open the control valve, the air supply will apply pressure to the balancing bellows, causing it to expand and oppose the expansion of the input bellows. If the pressure to the input bellows is less than the pressure in the balancing bellows, the instrument will overcorrect, creating an imbalance in the other direction. Now, this problem can be resolved by adding an exhaust line with a manual control valve. Then, by opening the valve in the exhaust line, we can bleed off the excess pressure until it exactly balances the pressure to the input bellows. The pressure being applied to the balancing bellows at this point is identified as back pressure. Now we can determine how much back pressure is applied to the balancing bellows by adding an accurate pressure gauge. When this instrument is balanced, as indicated by the error detector, the back pressure is the same as the input pressure. In effect, we've measured the unknown input pressure by measuring the back pressure. And so far, we've seen two examples of how the balancing principle works. One using a simple weight scale, and the other using an illustration to identify the basic mechanisms found in pneumatic instruments. Now, you'll remember that I said pneumatic instruments are self-balancing. In a self-balancing instrument, the output is changed automatically rather than manually until an error is corrected and balance is restored. So let's look at an illustration of a pneumatic instrument that is self-balancing. It balances itself. Now, this illustration is similar to the previous example, except that the supply and exhaust valves in the balancing mechanism are arranged so that the error detector positions the valves. It works like this. When an unknown pressure is applied to the input bellows, several things happen. The bellows expand, causing the error detector to move, which opens the supply valve and closes the exhaust valve, diverting the air supply pressure to the balancing bellows. As back pressure builds, the balancing bellows expands, opposing the expansion of the input bellows. This causes the error detector to move in the opposite direction, restricting the flow of supply air and venting excess pressure through the exhaust line. The mechanism will momentarily fluctuate in this manner until the instrument eventually reaches a balanced state, where the pressure in the balancing bellows balances the pressure in the input bellows. The pivot in this example is centered exactly between the input and balancing bellows. So when this instrument is balanced, the back pressure, as indicated on the gauge, is equal to the input pressure. Well, that's basically how a self-balancing instrument works. When an unknown input is applied, an error is detected and the output is automatically changed until balance is restored. By calculating or measuring the change in the output of a pneumatic instrument, we can determine how much the input changed. Now, up to this point, we've looked at a scale and simplified illustrations of pneumatic instruments to describe the self-balancing concept. Basically, the arrangements of the input, error detector, and balancing mechanisms were similar for the scale and the illustrations. But as you'll see later, the arrangement of these mechanisms varies widely in actual self-balancing pneumatic instruments. In addition, self-balancing pneumatic instruments can include a variety of parts besides just the balance beam, pivot, and bellows that we saw in the simplified illustrations. As we'll see later, the operating parts can include links and levers, springs, diaphragms, gears, and other parts. When we return, we'll look at some of these components and how they're arranged in more detail. But first, review your text. Be sure you understand the basic concept of how a self-balancing instrument works before continuing. So far, we've identified the basic mechanisms found in pneumatic instruments: input mechanisms, error detecting mechanisms, and output or balancing mechanisms. The main components that we've looked at include bellows, beams with pivots, and valves. But if we look inside a pneumatic instrument, like this one here, you'll see that there are many different shapes and kinds of components besides bellows, beams, and valves. Now, no one instrument contains all the different kinds of components. So to give you an idea of the variety, I've collected some of them that we've had here in the shop. Here we've got levers, beams, springs, bellows, gears. Just a small collection of the variety of parts you may find in pneumatic instruments. All of these components can be used by an instrument to convert the condition of a process variable into readable or usable information. We don't have time to examine each of these, so we'll concentrate on the three that are most common in pneumatic controlled instruments: levers, beams, and springs. First, let's discuss just what a lever is. A lever consists of any rigid bar or rod arranged in such a way that it can pivot about some definite point. Levers are generally worked on by two different and opposing forces. One force that we'll refer to as the effort force attempts to move the lever in a specific direction. The other force, which we'll refer to as the resistance force, resists the attempts of the effort force to move the lever. Now, if the effort force is great enough, it will overcome the resistance force and move the lever. The way this is done depends on the kind of lever used. Essentially, levers can be divided into three groups. It's not essential that you know which group a particular lever belongs to, but that you understand that there are a number of ways in which levers can be used. For example, this diagram represents the first group. This lever has its pivot located between the resistance force and the effort force. In this particular case, the pivot also happens to be exactly centered between the resistance and effort forces. However, the pivot doesn't have to be exactly centered. For example, the pivot could be closer to the effort force. In this position, it would take a greater effort force to balance a smaller resistance force. Or the pivot could be located closer to the resistance force. In this position, it would require less effort force to balance the same resistance force. This is the most common use of this type of lever, to overcome resistance forces with less effort. Here are two simple examples of this first group of levers. On this scale, this is the pivot, and this is the lever, which I referred to earlier as a balance beam. The resistance force is the unknown weights in this tray, and the effort force is the known weights in this tray. Notice that in this scale, the pivot is centered exactly between the resistance and effort forces. These pliers are another example of this type of lever. Here's the pivot. The resistance is whatever you grip with the pliers, and the effort is the squeezing action of your hand on the handles. Notice that the pivot is closer to the resistance than to the effort. So in general, the pivot of this first group of levers is located between the effort and resistance forces. This is a diagram representing a second group of levers. Like the first, it's often used to overcome resistances with less effort. This lever has the pivot at one end and the resistance between the pivot and the effort. The wheelbarrow is a simple example of this group. It has a pivot at the wheel. The effort is supplied by the person lifting on the handles, and the resistance is the weight located between the pivot and the effort. So in the second group of levers, the resistance force is applied between the pivot and the effort force. A third group of levers, on the other hand, has the pivot at one end of the lever and the effort between the pivot and the resistance. With this lever, it takes a greater effort force to balance a given resistance force. Unlike the first and second groups of levers, the primary purpose of this lever is to produce a large motion from a small motion. For example, a small amount of motion at this point results in a large amount of motion at this point. Tongs are an example of this group of levers. The pivot is at one end, the resistance is the object being picked up, and the effort is the squeezing action on the arms of the tongs. Now, the examples we've seen of levers are okay as far as that goes, but you're more likely to find levers like these in pneumatic instruments. Now, these levers can be divided into two categories: two-sided and one-sided. Now, both of these levers are two-sided. They belong to the first group of levers because the pivot is located between the effort and the resistance. For example, with this two-sided lever, an input or effort force on this side causes the lever to rotate on its pivot, moving the output or resistance force on the other side. Now, with this two-sided lever, a vertical input motion here results in a horizontal output motion here. Now, this is a one-sided lever. This design more closely resembles the third group of levers. Here, the input comes through the shaft or pivot. As the shaft rotates, the lever rotates. The effort is a result of torque or twisting action applied to the shaft. The input shaft acts as both the pivot and effort force. The output or resistance force is the work that's being done at the end of the lever. Usually when you hear somebody mention levers in reference to pneumatic instruments, you'll also hear them mention links and levers. Now, a link is simply a device that connects a lever to another lever or mechanism, as in this example here. As you can see, the length of this link is adjustable. Often this adjustment is made when this instrument is being set up or calibrated. As you work on various pneumatic instruments, you're going to find combinations of links and levers different than the ones we looked at here. You'll also see two other kinds of components that I said we'd look at: beams and springs. Now, a beam is similar to a lever, except that it's usually thicker and heavier, more rugged for heavy-duty work. Also, beams are seldom bent at an angle. They're usually straight and rigid. Otherwise, they swivel on a pivot like a lever and perform similar functions. Well, that leaves us with springs. There are many different sizes and shapes of springs to be found in pneumatic instruments, but their basic purpose is the same: to move a precise distance in response to a known applied force. Let's look at a couple of examples. Now, here we have two types of springs: coiled springs and straight springs. Straight springs are typically fixed at one end. When a known force is applied to the spring, it will move or deflect a specific distance. And every time the same force is applied, the spring will move the same distance. When the force is removed, the spring returns to its original shape. Generally speaking, long straight springs will deflect a greater distance than shorter ones, and thinner springs are typically more flexible than thicker springs of the same material. Now, these rules of thumb about length and thickness in straight springs also apply to coiled springs. In addition, coiled springs with large diameters are more flexible than coiled springs of the same material with smaller diameters. Now, generally, coiled springs can be divided into two categories: those that are specifically designed to resist compression and those that are designed to resist extension. Now, both kinds of coiled springs have the same purpose that all other springs have, and that is to deflect a precise distance for a known applied force. They're just designed to move in different directions. So, when you take the cover off of any pneumatic control instrument, you may find any number of different shapes and sizes of springs. For example, in this positioner, this spring is designed to oppose the deflection of the input bellows and beam. Now, in addition to different springs, you'll also find a variety of beams, links, and levers, as well as some of the components we didn't look at in detail: bellows, gears, and so on. And in self-balancing instruments, these components can be a part of the input, error-detecting, or output balancing mechanisms. And we'll be looking at some of these components in more detail throughout the rest of this program. But before we continue, read the material in your text. When we return, we'll look at various input mechanisms. Pneumatic instruments, such as controllers, transmitters, and positioners, all have input, error-detecting, and output balancing mechanisms. Now, these are the mechanisms that together make these instruments self-balancing. Before we look at specific input mechanisms and see how they work, let's briefly review the self-balancing concept. Now, in this illustration of a simple self-balancing pneumatic instrument, the main components include an input bellows, a balance beam, an error detector with its air supply, an output or balancing bellows, and a gauge which indicates the amount of back pressure. When an unknown pressure is applied to the input bellows, it expands, lifting the balance beam and moving the error detector. This opens the supply valve and closes the exhaust valve, diverting pressure to the balancing bellows. As back pressure builds, the balancing bellows expands, opposing the expansion of the input bellows. This causes the error detector to restrict the flow of supply air and return the instrument to a balanced state. Now, throughout the rest of this program, we'll be looking at the three basic pneumatic instrument mechanisms: We'll start first with input mechanisms. Now, we have a number of pneumatic instruments here in the shop that we can use to identify 3 or 4 different kinds of input mechanisms. Now, let's start with this positioner. Now, a positioner frequently is used to adjust air pressure to an actuator, which physically moves or positions something, such as valves or louvers. To do this, the positioner receives an input signal from a controller or a manual control station. Now, we move this cam out of the way so that we can see what the input mechanism is in this instrument. Now, this bellows is the input mechanism. It's connected to an air pressure line that feeds a pneumatic input signal to it. The input bellows is also attached to this balance beam, which positions the error detecting mechanism. We can see how this input mechanism works using a simple illustration. The input signal from another pneumatic instrument, such as a controller, is fed through this air pressure line and into the input bellows. Assume, for example, that the input pressure is 6 psi, and that at 6 psi the positioner is balanced. Well, what happens if the input pressure changes, say to 8 psi? Well, the bellows expands, lifting the balance beam, which is pivoted on this end. Now, the other end of the balance beam is attached to the stem of a pilot valve. The pilot valve represents the error detecting mechanism for this positioner. With the balance beam and pilot valve stem lifted up, the positioner is out of balance. At this stage, the output balancing mechanism comes into play to restore the balance. We'll see how various error detecting and output balancing mechanisms work later. But for now, let's look at another input device, this time in this temperature transmitter. Actually, this transmitter is fairly common. The process that this particular transmitter monitors is temperature, although it could easily be used to measure pressure as well. The input mechanism in this transmitter is different than the one in the positioner. It's this spiral Bourdon tube right here. This second tube compensates for temperature changes surrounding the transmitter, which for our purposes we don't need to be concerned with. Instead, we'll concentrate on this first Bourdon tube, which is the input mechanism for this transmitter. Now, I'm not suggesting that positioners have bellows for input mechanisms and transmitters have Bourdon tubes. Another transmitter could just as easily have a bellows rather than a Bourdon tube. But because of the design of this particular transmitter, a spiral Bourdon tube is a more practical input device. Well, let's see how this transmitter works. This simplified illustration shows basically how the Bourdon tube input mechanism works. Here, a temperature sensing bulb is connected by a capillary tube to the Bourdon tube. This whole arrangement, the temperature bulb, capillary tube, and Bourdon tube, can be filled with any one of a number of specific liquids or gases that expand when exposed to heat. This is referred to as a filled system method of temperature measurement. And it works like this. Say that the temperature bulb is sensing changes in temperature. When the temperature increases, the material inside the bulb expands, creating a small amount of pressure that expands equally throughout the filled system. This pressure change causes the tip of the Bourdon tube to move in proportion to the change in pressure. The tip of this Bourdon tube is connected by a series of links and levers to the error detecting mechanism, which in turn is connected to the output balancing mechanism. Again, we'll look at how balance is restored by error detecting and output balancing mechanisms later in this program. So we've seen 2 different input mechanisms, one that uses a bellows and one that uses a Bourdon tube. Now, this differential pressure transmitter uses still another kind of input device, a type of diaphragm, which is encased in this housing. We'll use a cutaway of this device to identify the internal parts. The diaphragm here senses changes in differential pressure between a high pressure and a low pressure. The high pressure is conveyed to one side of the diaphragm through this port, and the low pressure is conveyed to the other side of the diaphragm through this port. We can see how this works using a simple illustration. Here, the differential pressure transmitter has been connected to a pipe that has a fluid flowing through it. Inside the pipe is a flow element or restriction. When the fluid flows through the restriction, pressure is higher on the upstream side than it is on the downstream side. A difference in pressure or differential pressure is created across the restriction. The transmitter is connected to the pipe on both the high and low pressure sides of the restriction. The high pressure is conveyed through tubing to a port on this side of the diaphragm. The low pressure is conveyed through tubing to a port on this side of the diaphragm. A change in the difference between these pressures would cause the diaphragm to move a minute amount. For example, if the flow through the pipe increased, the differential pressure would increase, and it would move the diaphragm just a small amount in this direction. In this way, the diaphragm acts as the input mechanism for this transmitter. Now, the diaphragm is connected by this link to a beam called the force beam. When the diaphragm moves, it pivots the force beam a small amount, which in turn causes the output of the transmitter to change. So, with these three instruments, we've seen three kinds of input devices: a bellows, a bourdon tube, and a diaphragm. Now, these are some of the more common kinds of input mechanisms, but there are others, like the input mechanism in this flow transmitter. Now, we don't have to look at this instrument in detail, but essentially, this transmitter is attached to a meter. Inside the meter body is a primary element, which converts changes in the process to mechanical motion. Now, this motion causes this shaft to rotate, and the shaft is connected to the transmitter by this link so that the rotating motion acts as the input to the transmitter. So you see, in self-balancing instruments, there are many kinds of input mechanisms. As we'll see later, when an input mechanism moves in response to a process change, it's the amount of movement that is sensed by an error-detecting mechanism, which changes the output of the instrument. We'll look at some of these error-detecting mechanisms next, after you take time to read the material in your text. As we've discussed, the essential components of a self-balancing instrument are an input mechanism, an error detector mechanism, and an output balancing mechanism. But it's the error detector that is the heart of any self-balancing instrument, whether the instrument is a controller, positioner, or transmitter. Let's go back to the illustration of a simple self-balancing pneumatic instrument. Now, in this instrument, this is the error detector. When the input bellows lifts the balance beam, it causes the error detector to open up the air supply line and restrict the flow of air through the exhaust line. Restricting the exhaust allows the flow of supply air to build a back pressure that eventually expands the balancing bellows and balances the instrument. The function of an error detector is to convert a small mechanical motion created by the input mechanism into a proportional back pressure. What happens is a change in a process variable is converted to a mechanical motion by the input mechanism, and the mechanical motion is converted to a back pressure by the error detector. Now, later we'll see how this back pressure is sometimes used by the balancing mechanism to balance the instrument, and how other times the back pressure is used to generate an output signal as well. Now, there are a number of different arrangements or variations of error detector mechanisms. However, generally speaking, they can be divided into two basic types: flapper nozzle and pilot motion detectors. Now, let's look at a flapper nozzle arrangement first and see how it appears in this temperature transmitter. Now, here you can see the flapper and the air nozzle. The flapper is positioned by the movement of this lever. Using a simple illustration, let's see how a typical flapper nozzle error detector mechanism works. First, let's identify the elements that are present in flapper nozzle mechanisms. They are a nozzle, the flapper, a link that connects the flapper to an input mechanism, an air supply, a fixed restriction, and a back pressure compartment. Basically, the mechanism works like this. Instrument air flows through the restriction, through the nozzle, and is forced against the flapper. Where the input mechanism positions the flapper determines how much pressure develops in the back pressure compartment. Normally, this back pressure is the signal representing the condition of the process variable that goes to the output mechanism. But to demonstrate how a typical error detector mechanism works, we'll attach an accurate pressure gauge in place of an output mechanism. Now, the amount of air flowing through the nozzle and consequently the amount of pressure in the back pressure compartment, as indicated by the gauge, is varied by the movement of the flapper. For example, the flapper may be positioned away from the nozzle. This would allow air to flow almost unrestricted from the nozzle, resulting in a decrease in back pressure. On the other hand, the flapper could be positioned close to the nozzle. This would reduce the flow of air from the nozzle, increasing the back pressure. Each time the flapper is positioned, whether it covers or uncovers the nozzle or any position in between, it results in a back pressure that is nearly proportional to the distance of the flapper from the nozzle. Now, the purpose of the restriction is to reduce the forcing effect of the supply air flowing against the flapper. For example, if the air supply is flowing without a restriction against the flapper, it would force the flapper away from the nozzle. This would make it impossible to position the flapper and vary the amount of back pressure. As a result, the instrument would not be able to do what it's intended to do, whether it's supposed to transmit, control, or whatever. With the restriction in place, the air supply is reduced, but it still provides a constant flow of air to the back pressure compartment. The size of the opening in the restriction is smaller than the opening in the nozzle. So when the nozzle is uncovered, the volume of air that escapes through the nozzle is greater than the volume of air that flows through the restriction. Now remember that the function of an error detector is to convert a small mechanical motion into a proportional back pressure. And each time a flapper is repositioned, it is moved as a result of a change in an input mechanism, such as a Bourdon tube, bellows, or diaphragm. As we saw, in this temperature transmitter, the error detector is a flapper nozzle. The flapper is connected by a series of links and levers to a Bourdon tube input mechanism. Okay, now before we got into this whole discussion of flapper nozzle error detector mechanisms, I said that there are two basic types of error detectors. The type we looked at first was flapper nozzle devices. The other type we can see is in this positioner. Now, this error detector is an example of a pilot motion detector. Generally, when the input bellows expands, it lifts this beam, which positions a stem within the detector. We'll see how this works in greater detail later. Now, there are a variety of different designs of pilot motion detectors. They can be referred to by various manufacturers as pilots, pilot valves, relays, or relay valves. But generally, they work on the same basic principle. Two restrictions are simultaneously varied by a single mechanism. Let's look at an illustration of a simplified pilot motion detector, which we'll refer to from now on as a pilot valve. First, we'll identify the common elements, and then we'll look at how it works. The elements that are common to most pilot valves include two restrictions, a plug that can simultaneously vary the size of the two restrictions, an air supply, and a back pressure compartment with an output connection. Generally, the mechanism works like this. Instrument air flows in through this supply port, past the inlet plug restriction, into the back pressure compartment, around the exhaust plug restriction, and out the exhaust port. Instrument air also flows out from the back pressure compartment through this output connection. The amount of air flowing through the exhaust port, and consequently the amount of back pressure in the back pressure compartment, is varied by the mechanical movement of the plug. The position of the plug is determined by the movement of the input mechanism. We'll add a gauge to the output connection so that we can see how back pressure changes in relation to the operation of the pilot valve. For example, the plug could be positioned like so. In this position, the plug reduces the flow of air through the supply port and opens the exhaust port. As a result, less supply air is allowed to enter the back pressure compartment. Much of the existing back pressure is released through the exhaust port, causing the back pressure and output to decrease to almost zero. On the other hand, the plug could be positioned like this. Here, the plug reduces the flow of air through the exhaust port and opens the supply port. In this position, back pressure and output pressure builds. Each time the plug is positioned, whether it partially closes or opens the exhaust and supply ports, or at any position in between, it results in a back pressure that is nearly proportional to the position of the plug. Remember again that the function of an error detector is to convert a small mechanical movement into a proportional back pressure, and that each time a valve plug is repositioned, it is moved as a result of a change to an input mechanism. In this positioner, we saw that the pilot valve was connected by a balance beam arrangement to a bellows input mechanism. Now, this type of pilot valve is fairly common. We can look at a simplified illustration to see how it works. Here we have the main body of the pilot valve. It houses the back pressure compartment. This port is for supply air to enter. Now, unlike the illustration we just saw, this pilot valve has two output ports and two exhaust ports. The stem of the pilot valve is positioned by the movement of the beam. As the beam moves up, the stem either covers or uncovers the output ports, changing the output of the positioner. As the beam moves down, the stem moves, again changing the output. Now that takes care of the basic types of error detector mechanisms. First, we saw flapper nozzle devices, and then we looked at the pilot motion detector device. Remember that you'll come across variations as you work on different types of instruments. Now keep in mind that all along we've been looking at self-balancing instruments, and that all self-balancing instruments have input, error detector, and output balancing mechanisms. So far we've discussed the input and error detector mechanisms. We'll close for now so you can go through the material in your text. When we come back, we'll look at output balancing mechanisms. Earlier, I used this scale to show how a known weight is used to balance the weight of an object whose weight was not known. And we've seen how self-balancing instruments work on the same principle of balancing an unknown input with a known output. We've also identified various input and error detecting mechanisms by looking at instruments that are used to monitor, indicate, and maintain process conditions. In this part of the program, we're going to look at a simplified control loop to see how a controller is used to maintain a typical plant condition. In this illustration of a controller, you'll recognize some of the components we've been looking at, including an input bellows, a balance beam and pivot, and a flapper nozzle arrangement. You'll note that so far, the controller in this illustration does not have an output balancing mechanism. Let's see how this controller would attempt to maintain a process variable. First, without an output balancing mechanism. This will help us identify why output balancing mechanisms are needed. To do this, we'll connect the controller to a process. In this process, fluid flows through this pipe, and the flow is adjusted by a control valve. This symbol represents a flow transmitter that measures differential pressure across a flow element as an indication of flow. The transmitter converts differential pressure into an input signal which is sent to the controller. When there's a change in fluid flow through the pipe, the transmitter senses the change and adjusts its signal to the input bellows of the controller. For example, if the signal to the controller was originally 4 psi, when the flow increases, it may change to 6 psi. This pressure increase to the input bellows causes the bellows to expand, pivoting the balance beam and moving the flapper toward the nozzle. This increases the pressure in the back pressure compartment, raising it to its maximum value. This increased pressure then completely closes the flow control valve, stopping the flow of fluid through the pipe. As a result, the transmitter changes its signal again, causing the bellows to pivot the beam and flapper all the way open. Now, this reduces back pressure, which allows the control valve to open all the way. Without a balancing mechanism to counterbalance this controller action, the controller would continue to cycle. Now, needless to say, this is not very effective control for this process. Well, let's see what happens if we add a balancing bellows to this controller. Let's say that the signal to the input bellows changes, again from 4 to 6 psi. Again, the bellows expands, pivoting the beam and moving the flapper toward the nozzle. Only this time, the back pressure is transmitted to the balancing bellows as well as to the control valve. This back pressure in the balancing bellows lifts the flapper off the nozzle, counteracting the force applied by the input bellows until the input and output pressures are then balanced. Now, this output pressure adjusts the control valve until it precisely counteracts the original flow change, maintaining the proper flow. The kind of balancing function we've just seen is common to many pneumatic instruments where input change is balanced by the output change. Now, there's another term that you'll be hearing to identify this balancing aspect of pneumatic instruments, and that's feedback. Feedback, in this sense, means that a portion of the instrument's output signal is returned to the instrument in order to balance its input and stabilize its output. As you work with pneumatic instruments, you'll come across a number of ways in which the output is fed back to the instrument. But that's enough about balancing or feedback mechanisms. Let's take a few minutes to discuss the output of our flow controller. There are a couple of considerations having to do with instruments that use flapper nozzle error detectors. We can see what these considerations are using the controller illustration. In a flapper nozzle arrangement, the nozzle directs a flow of air against the flapper and to a small degree forces the flapper away from the nozzle. This pushes against the pivoting action of the balance beam caused by the expansion of the input bellows. If allowed to, the force of air flowing through the nozzle and against the flapper could throw off the balancing relationship between the input and balancing bellows. However, the forcing action against the flapper is reduced by using a restriction that cuts down on the volume of air flowing to and through the nozzle. But frequently, the output signal has to be transmitted a long distance to reach the final control element. With a small volume of air, it will take a long time for a change in output to reach the control valve. Somehow, the volume of air has to be increased to reduce the time it takes for the signal to reach the valve without increasing the volume of air pushing against the flapper. Now, this can be done by replacing the regular nozzle with a signal boosting device like this pneumatic relay. Devices like these are sometimes referred to as a pilot valve or pilot relay, again depending on the manufacturer. This relay now functions as both the error detecting and output mechanism for the controller. Let's move in closer to this relay so we can see how it works. You can see that the relay is divided into two compartments by a diaphragm. Air is supplied to both compartments, but the airflow path to the upper compartment includes a restriction that limits the volume of air flowing to the nozzle. The airflow path to the lower compartment has a variable restriction, like the valve plug we saw when we looked at the pilot valve error detector. This allows us to increase the volume of output air without increasing airflow volume to the nozzle. In this way, air is allowed to flow through both the fixed restriction to the nozzle and the variable restriction to the final control element. Let's see how the relay works when the signal to the input bellows increases. As before, the input bellows expands, pivoting the beam and moving the flapper toward the nozzle. This increases the pressure in the upper compartment of the relay, which pushes down on the diaphragm and moves the plug so that more air flows to both the balancing bellows and to the control valve. The balancing bellows expands, positioning the flapper above the nozzle. This regulates the pressure in the upper compartment, allowing the diaphragm and plug to stabilize at their new positions, and increases the flow of air to the control valve. When the pressure in the line to the control valve reaches the desired value, the relay and the instrument will be in balance. Now let's see how the relay would respond should the signal to the input bellows decrease. This would represent a decrease in flow. In this case, the input bellows contracts, pivoting the beam and moving the flapper away from the nozzle. This decreases the pressure in the upper compartment of the relay, which allows the diaphragm to rise and moves the plug, reducing the flow of air to the lower compartment. The excess output pressure bleeds off through the exhaust port of the relay and decreases the flow of air to the control valve. The balancing bellows contracts, repositioning the flapper above the nozzle. This regulates the pressure in the upper compartment of the relay, allowing the diaphragm and plug to stabilize at their new positions. When the pressure in the line to the control valve reaches the desired value, the relay and the instrument will be in balance. Well, now that you understand the function of output or balancing mechanisms, let's take a minute to identify the output balancing mechanism in this differential pressure transmitter. Again, we'll use a cutaway to identify the internal parts. You'll remember from when we looked at this transmitter earlier that it has a diaphragm input mechanism which converts the difference between a high and low pressure into a mechanical motion which pivots this balance beam. The motion of this balance beam positions a flapper nozzle error detecting mechanism which changes the pressure in the nozzle back pressure compartment. This change in pressure operates a pneumatic relay. In turn, the relay, acting as an output mechanism, creates an output pressure. This pressure is sent to another instrument as well as to this balancing bellows, which is the balancing mechanism for this transmitter. The bellows expands or contracts to balance the differential pressure change to the diaphragm input mechanism and return the transmitter to a balanced state. So by now, you should know how input, error detecting, and output balancing mechanisms work. You should also have a pretty good idea now of the basic kinds of components you'll find in most self-balancing instruments, and generally what they do. Now, this knowledge, plus the manufacturer's data, should help you to recognize components and mechanisms in pneumatic instruments that you've never seen before. Now, this is an important first step in learning how to repair and adjust pneumatic instruments in your facility.